The electrochemistry of lithium batteries. Lithium batteries are prevalent in nearly every sector of technology. They are very useful in transferring energy and have become a staple in energy consumption. There are various types of lithium cells, consisting of both primary and secondary cells, both of which are used to power our world.
Johann Arfwedson first discovered lithium in 1817 in Jan Berzelius's personal laboratory. Soon after, the battery capabilities of lithium were discovered by the mid-20th century. Roughly 100 years later, the first lithium battery was brought to markets similar to the primary cell featured on the left. Along with Dr. Whittingham's help, Sony then commercialized the lithium-ion battery in 1991. There are two categories of batteries, primary and secondary cells. Primary cells are single-use, cylindrically shaped batteries which are commonly used in toys and remotes. These are referred to as lithium cells. Secondary cells, known as lithium-ion batteries, can be recharged by running a current reverse to the flow of electrons to reverse the reactions. However, secondary cells are not perfect. Some of these battery capacity is lost every time it's recharged, diminishing the total lifespan of the battery with every charge. Primary cells are cheaper initially, but over time, lithium batteries can be the more economical choice since they can be reused over and over again, unlike primary cells.
Similar to most batteries, lithium batteries are made with a cathode plate, an anode plate, and a separator immersed in an electrolyte. In a lithium-ion battery, the anode is almost always graphite, while the cathode varies based on the model of battery. The electrolyte separator is usually polymer. Within a lithium metal battery, the anode is lithium metal, with the cathode again varying depending on the preferred molecule. The figure on the bottom shows how, in general, the actual battery will have metallic tabs added to the anode and to the cathode, acting as connectors between the plates and the terminal. Since, as will be discussed, these batteries can be dangerous, multiple safety features are added. This includes vents to prevent heat and pressure from building up, a positive temperature coefficient and circuit interrupt device, with which both cut the positive terminal off from the inner plates should the temperature rise too high, and some batteries may even have a protection circuit board, which can be programmed to do various things under different circumstances. The chemistry of lithium-ion batteries, specifically based on lithium manganese dioxide. Lithium manganese dioxide, LiMn2O4, is a spinel structure of space group FD3M, an OH point group, structured in a cubic close packed array. The oxygen ions are at the 32E position, the Mn ions are at the 16D site and have an octahedral coordination to the oxygens, and the lithium ions are situated at the 8A tetrahedral site at the edge of the octahedron next to the vacant 16C sites. This all contributes to a very strong and stable structure. When in a battery, lithium atoms will be sent to the spinel from the anode. When these lithium ions are inserted into the spinel, they intercalate and occupy the 16C sites. When this occurs, the lithium ions already in the 8A tetrahedral site are displaced into the nearby vacant 16C site, inducing a first-order phase transition. This causes the manganese to be reduced, and as this reduction occurs, a Jan teledistortion occurs and the manganese 3D orbital splits. This causes the symmetry of the crystal structure to decrease from cubic to tetragonal. The graph in the middle shows this Jan-Teller orbital splitting, and an energy release of magnitude epsilon can be seen. This energy is what powers the cell and makes the battery work. In the top left, other types of battery structures and configurations are depicted. The layered lithium cobalt dioxide has octahedral site lithium ions, but it has a smaller cell voltage compared to the spinel lithium manganese dioxide. There are also polyanion oxide molecules with an even greater voltage capacity, but are not too commonly used. Part A of the figure in the left shows how lithium diffuses from octahedral sites to neighboring octahedral sites in the lithium manganese dioxide cathodes. Part B of this graph shows the lithium diffusion from one 8A tetrahedral site to a neighboring 8A tetrahedral site. The chemistry of lithium metal batteries, focusing again on lithium manganese dioxide, MnO2. The anode of the lithium metal battery is always lithium and is inserted into the lattice of the cathode, reducing the metal. In the case of lithium manganese dioxide batteries, manganese is reduced from 4+ to 3+. The overall battery reaction is shown in the middle, with the lithium ion being dissolved in the cathode. The manganese dioxide needed for these batteries is synthetically made and is called electrolytic manganese dioxide, or EMD for short. manganese dioxide can be made from the electrochemical removal of lithium from lithium manganese dioxide. Because of this, it maintains its spinel framework and structure seen in the previous slide. The figure on the left shows the structures of manganese dioxide polymorphs. The beta manganese dioxide, aka pyrolusite, is situated on top. The rhamnolite polymorph is below it, and these two are combined using heat to create the desirable EMD gamma manganese dioxide shown on the bottom. When the lithium ions are intercalated with the gamma manganese dioxide, energy is expelled and the crystal lattice expands, causing irreversible structure changes, hence why this battery is disposable and cannot be recharged.
Lithium has many advantages, one of which is its low negative redox potential. This favors reductions, which makes it an ideal cathode material for batteries. Lithium also has a high specific energy, which is the ratio of energy to weight a battery possesses. This allows lithium cells to be very lightweight while also providing plenty of power for consumption. Lithium ions can also travel freely throughout the cell, so regardless of the charge state of the battery, the output voltage will remain the same. When compared with common alkaline batteries in the graph above, the voltage of the lithium batteries holds constant as the battery is discharged over time. This can be useful if certain devices need to maintain a certain level of voltage to operate correctly. For example, a device that must maintain 1.2 volts to operate. Lithium can also be used in both liquid and solid electrolyte systems, further increasing its applicability in commercial settings. Lithium's high charge-to-mass ratio makes it ideal for portable equipment. Its constant output is also useful in devices where voltage drops cannot be tolerated, such as medical equipment or security systems. Lithium-ion batteries can also be made to custom-fit devices such as cameras or phones. This custom fit can benefit things like cameras or phones where small compact batteries are required instead of a large cylindrical cell. Lithium batteries are increasingly being used in electric vehicles due to their lightweight design, rechargeability, and manufacture cost. Lithium cells also are widely used in solar energy and generators. Lithium batteries are susceptible to fires, thermal runaway, and violent venting, which can be catastrophic to life and property as indicated in the pictures above. Thermal runaway occurs when the temperature passes a certain threshold in the battery and it causes a chemical reaction that releases energy stored in the cell, further increasing the temperature. If there are many batteries connected to each other, this can cause a chain reaction of increasing temperatures that can be very dangerous and difficult to stop. Overcharging the batteries can also cause these events to occur, and this is when a battery is charged to a higher voltage than it is rated for. Adverse environmental conditions can also cause these events to occur, which can limit the applicability of these batteries in extreme weather conditions. Lithium cobalt dioxide cathodes can degrade under high voltages, which can cause oxygen gas to release to the system. This gas, along with the organic solvents that the electrodes are typically dissolved in, can provide ample fuel for fires to break out in the cells given the right conditions. This issue can be solved using a spinel-type cathode such as lithium Mn2O4, as oxygen is not easily released due to its structure. The spinel structure is also stable under high voltages and as such does not degrade the cathode and release oxygen gas to the system.
As shown, lithium batteries can be very dangerous, yet despite this, they are still widely used in the energy sector. This is because they are more lightweight, have a higher energy density, and are better at recharging than other batteries. Many of the batteries suffer from the memory effect, which is caused when a previous incomplete discharge occurs and reduces the capacity of subsequent charges and the overall battery life. This doesn't mean lithium batteries are used in all energy sectors, however. Alkaline batteries dominate the consumer disposable market. They are cheaper, have virtually no explosions, and are able to vary their energy output, making them useful for things like camera flashes. Further, cars have maintained the use of lead-acid batteries, despite lithium car batteries being available. This is again because lithium is too expensive, but also because lithium batteries require special care and protection and are not as robust as lead-acid batteries.
All batteries undergo a process called self-discharge, where they gradually lose charge over time due to internal reactions in the cell. This is why your phone may lose charge over the course of the day, even if you weren't using it very much. This process can also be sped up by higher temperatures, which is one of the reasons it is recommended to store batteries at low temperatures. The graph shows some various storage conditions and the self-discharge rates in a lithium cell over time. Lithium batteries will usually lose 8% of their charge in the first month of storage and 2% in all the following months. This drop is due to a buildup of film surrounding the lithium anode, which slows the internal reactions in the cell. Over-discharge can occur when a battery is discharged below its lowest safe limit for voltage. This can occur if the battery is also stored for extended periods of time. This can negatively affect the life of the battery and cause permanent damage to the cell, and so it is recommended to periodically charge the battery to ensure longevity. Lithium's self-discharge rate is relatively low when compared to other popular cells such as nickel-cadmium. Nickel-cadmium cells have a discharge rate of 15% the first day, and then 10 to 15% every following month of storage, making them less than ideal for long-term storage when compared to lithium.
There are many upcoming lithium battery discoveries and inventions. Firstly, conversion reactions are currently under development. They yield a matrix of binary molecules but contain large voltage hysteresis, which is when electron voltage changes, but the effects of the changes are delayed. This causes detrimental effects on the ability of the battery to maintain its charge. This type of reaction cannot be commercially used in batteries until this challenge is overcome. Another very important development occurring is the replacement of graphite as a standard anode in lithium-ion batteries with silicon. Lithium-silicon batteries would be able to revolutionize batteries, as they are capable of holding up to 10 times more energy than a standard lithium-ion battery. Because silicon bonds very rapidly and readily to lithium ions, it is able to be charged incredibly fast. Currently, it is not stable and collapses when in use, but promising advances are aiming to fix this. Finally, researchers are developing a vertically aligned carbon nanotube electrode, which will be able to increase battery power 10 times, increase battery lifetime by 5 times, and triple the energy storage capability. They could also decrease charging time tremendously. The demand for lithium will continue to increase exponentially over the next decade as emergent technologies develop and reach the consumer market. Lithium cell technology will lay the foundation for the next generation of discovery.